Okay, so I've posted up the final exam review document. That's on Slack. It's probably easiest to get there. I've reposted project number 2 yet again, and the yet again is because I'm just combing through the task descriptions, trying to fix some bad grammar and clarify some things to hopefully make it easier to make your way down through the tasks. And what else did I push up there? I think that's it. That was 3 items. Well, it's going to be 3 items once I push the solutions up there, but on Slack there are 3 new items up there. So those items are, close this down, the quiz, which I put solutions up for right away in case I can't get all the way through it today. Repush this, just making improvements in the task descriptions, and then their final review. So my plan for the day is to finish Appendix A, and then we'll come on to the final review and then see where we go from there, like talking about the project. No one's asked me any more questions since yesterday, and Chris, you've been the only one to ask me questions, but your questions have been good. But let's just get on with wrapping up the chapter and then see where we can go from there. So we left off with this relationship, which will be used in a number of the homework problems and examples, that tells us what the noise power available from the output of a system is, given its noise temperature, TE, and the relationship between TE and noise figure is really established right here. I didn't really point that out. It shows up, I think, in the next page. But the important thing about this effective noise temperature relationship is this tells us how to convert between noise temperature of a subsystem and noise figure. And we go back and forth between that and some of the calculations. And of course, this is always, unless said otherwise, is going to be 290 degrees Kelvin. So that's just a conversion parameter. But then this equation down here is important because if we're modeling a system and want to find the noise power at the output of that system, the available noise power at the output of an equivalent system that has some temperature TE and it has some noise temperature of the input, TS, then we can get the noise power in dBW or dBm that's sitting there at the output. And when we do our link budget analysis a little bit later from now, we'll have a received signal power. Well, we'll have a transmit power from the transmitter. We'll have some free space path loss. And then we'll have antenna gains on the transmitter and the receiver. And then we'll know what the gain is. If we know what the gain is down here, G sub A, then we'll be able to get the signal power at the output too, due to the received signal power at the antenna through the gains and so on, then the gain through the electronics front end, and then we'll be able to get the signal power, and then we can look at signal to noise ratios at that point, because we'll have both quantities of interest, how much noise power is present and how much signal power is present. Before we actually go on to that phase of the development, we're going to just look at this important equation set called cascade of subsystems, which is a pretty standard development. Like I said, I think Professor Song might teach this in her EMAG 2 class, and some of you maybe had that class last fall. I don't know. A lot of you, if you're a junior, you're taking the first semester of EMAG right now, but I think she does this in her second semester class because it fits in that subject matter, and it also fits here because of comm systems modeling. So the cascade works for any number of subsystems, but here it's just shown for 2 subsystems, but it can be generalized up to as many subsystems as you might have. And it shows that there's a temperature of a source which is driving this. That will become an antenna here eventually. And then we have the first subsystem is number 1, the second subsystem is number 2. And the idea is to be able to calculate the noise at the output due to the input, but along the way what we're going to do is we're going to get the effective noise figure of the cascade. So we're after characterizing this as either an F cascade or T effective cascade. And so the equations are, well, what we're looking at is we're saying that there's amplified noise from the source. That's number 1. That's coming through the gain of the first 2 subsystems, the temperature of the source, and then the bandwidth that everything's flowing through. And then we have noise, internal noise from amplifier 1 that is referenced to its input. So it's referenced to its effective noise temperature at its input, and that goes through the gain of the 2 stages and comes out as some internal noise. And then we have internal noise of amplifier or stage 2 reference to its noise temperature at its input, which is this TE2. And then that sums in. So we've got 3 things coming together. And the math just says that the noise power at the output then is the noise temperature of the source plus the noise temperature of the first stage effective, and then the noise temperature of the second stage referenced. It's referenced at the input, so that's why divide by the gain of the first stage to get everything referenced to the input. But this is just the development of the theory and showing that this equation, known as Free's equation for cascading subsystems, boils down to these 2 equations in the blue box. So this is the primary equation. It just tells you what the noise figure is going to be based on the noise figure of the cascade, based on the noise figure of each subsystem, 1, 2, 3, and so on, and the gains of the subsystems, 1, 2, 3, and so on. And then the secondary equation is the effective temperature of the cascade, and that can be calculated using the effective noise temperatures of each subsystem. But along the way, what you can do is you can work it either in terms of noise figure or noise temperature, effective noise temperature, and then you can come back to converting, if you want to, through this equation over here, which I'm going to write down next, right in here. That was F is equal to 1 plus TE over TO, the room temperature value. So you can convert back and forth if you want to. Most of the time my preference is to work in what I call the primary form with noise figures and gains, because that's generally closest to what you're given. And then if somebody wants you to get noise temperature, then you just work that from this equation, because you can spin this around if you want to solve for TE. And if I wanted to just do that right here, I could just see that TE is going to be F minus 1. That quantity times T0 will give you TE. So you can flip back if you want to, or you can flip everything to noise, all the subsystems to noise temperatures if you want to. You can do it any way you want, and sometimes I work problems 2 different ways just to see that I'm getting pretty much the same answer. Before we actually work a full-up example, we're also going to do one little investigation, and this is just to set the stage for a certain type of component known as an attenuator. And the attenuator is a subsystem where you put signal into it and the signal that comes out gets attenuated or reduced in power level by whatever the attenuator or attenuation value is. So if you put in 0 dBm into a 10 dB attenuator, at the output you'd measure minus 10 dBm. Generally, you don't use attenuators in a receiver front end unless there's something really bizarre that you have to deal with, like a strong signal or something, because attenuators do something really bad, and we're going to see what that is here in just a second. But another application of attenuators is as a padding mechanism to help match impedances, and I've used them for that before in one of my jobs, my first job actually. We would use attenuators, also referred to as pads, because you use an attenuator to pad two circuits so they don't interact with each other. But here's what's bad about the attenuator. If we look at what the attenuator is going to do, the effective noise temperature of the attenuator is, instead of having a gain GA, we actually have 1 over L for the attenuator. So L is the attenuation value, and so if it attenuates by a factor of 2, L would be 2, and the gain would then be 1/2. So we put that into our model to find the noise power at the output, and what we're looking to do for this single component, where we're looking at what the impact of the attenuator is, we get an expression that says the following. When we look at our expression for the output power of the cascade, we see that we have the term that I have the brace underneath is the noise power relative to the input. That's what that referencing is doing. And then we put the gain onto it and we get the noise power at the output. So if I look at that, it's looking like the noise temperature, since the output noise power is KTS times B to begin with, it's telling us that if I make the substitutions in there of dividing through by K and B, that it looks like we have this equality holding for the case of the attenuator. And if we spin that around, then we see that the effective noise temperature of the attenuator is 1 minus the attenuation times TS. And since we know noise figure is defined as 1 plus TE over T0, if we plug in the attenuation, well, if we plug in this value for the noise temperature, TE, which is what I've done right here, just set that in the top, then for an attenuator at room temperature, the noise figure is identically the attenuation value. So if you have a receiver front end that starts with an attenuator and it's got, say, an attenuation of 60 dB, then the noise figure of that receiver front end is 60 dB, which is really bad. It says it's very noisy, and intuitively what it's saying is if the first thing the received signal sees is an attenuator, it's just dropping the signal level down closer to the thermal noise floor, and it's pretty much ruining things. It's making things sit closer to the noise floor. If you have amplification at the very beginning, then you keep the signal above the noise floor. Of course, it depends on how noisy that amplifier is, but in the case of the attenuator, it's just a bad situation. You end up with an immediate penalty in noise figure because of the loss. And that scenario comes about in a practical system because the very first component after the antenna could possibly be the feed line, which would be the cable that runs from the antenna to the receiver. And if they're not co-located, then you have a significant amount of cable And it doesn't have to be very much at a high frequency. It can only be, say, less than 10 feet or something, or just a few feet at a high enough frequency and that attenuation is going to give you a noise penalty hit, noise figure hit. And remember last time I was talking about the LaserCom system that I worked on in my first job. We put a preamp right behind the photomultiplier tube in order to have it reduce the noise penalty of driving over a cable. And in most satellite TV systems that you might have at your house, you'll have a preamp right at the backside of the antenna that's pointed out to the satellite, and that alleviates the noise figure penalty you would get from driving the cable directly.
They also have a mixer up there too.
Yeah, that's right. They have that.
Nowadays, because they don't come down. They don't come down to cable at X band or Ka band.
Yeah.
They come down to S band. So
And then
there's a mixer up there.
And that makes it easier to drive the cable too, because it's now at a lower frequency, right?
Yeah.
So that's just something to think about. And you might be curious as to how they power things. Well, they can send power over the RF cable itself. It's the same idea that audio recording studios use too. It's called phantom feed, where you actually send some power down the coax line, and that can drive the preamp. I was talking about that yesterday in my phase lock loops class, and we were going through an example of a GPS patch antenna, and then you have something called a bias T that sits at the receiver, and the bias T allows you to interject DC into the coax, but keep it isolated from the receiver front end through a blocking capacitor. And then the bias is fed in through a decoupling network to make sure that the RF impedance match doesn't get disturbed when you feed the DC into the cable. Does anybody else have an example of that, or can think of an example of something like that? It works in both audio and RF. So
Yeah, it's usually a coil, but it's kind of a pull-up inductive. That's what we use anyway. A lot of amplifiers do that as well.
what?
It's kind of like a bias T. Use like an inductor up at the. You send the DC down the cable,
Right,
and they come up through an inductor, and the inductor is like a choke,
right.
and it blocks the RF from there. But then you just decouple it with the capacitor.
Yeah, exactly.
Yeah.
Okay. Some of you are interested in that. Some of you have maybe experienced some of that, but yeah, decoupling is a common thing. Actually, it's a really important thing in RF. Decoupling of all kinds is important because power can pick up. You can get signals. You can get RF signals onto your power line, and then you've got a real problem because it can kind of go from one subsystem to another if you don't decouple things properly in the layout. Well, let's go through an example here of a receiving system, and this is one that's in the book. So the first scenario is going to be to have the feed line loss at the input, then the first RF preamp, then a mixer, then an IF amplifier. Just some subsystems that we can use in Free's equation here. Then the second go on this example will be putting the RF amplifier first and then putting the feed line second, as if to say we have the preamp out there right at the antenna, and then we'll get the signal gained up so the noise figure hit of the attenuator won't be so bad. So in this example, everything is given in dB. So we have the loss of the attenuator is 1.5 dB. So just to make sure that we're thinking our electronics properly, gain is going to be, of that device, is going to be what, if we wanted to get it in dB? You should just snap through your head, say, if I have a gain of something or another, I have a loss of the opposite sign. So I have a loss of 1.5 dB, that would be a gain of minus 1.5. So we'll use that in our calculation here in a moment. And then the noise figures are all given in dB. Well, the thing about Free's formula is everything up here, I'm just going to erase these things. All the values here are as ratios. There's nothing that's log 10 inside of here. So there's nothing that can be in dB. Noise figure can't be in dB. It just has to be a ratio of numbers, or just a number, period. So what we have to do before we can use Free's formula is we have to get everything out of dB and into ratios. So that means we have to convert everything. And the generic conversion would be G would be equal to 10 to the G in dB over 10. And it's because we're working with power ratios, so we use log 10 log base 10. So we take 10 to the G dB over 10 to get gain as a ratio. And then the same thing for F. F as a ratio is going to be 10 to the F in dB over 10. And once we do that, then we can move forward with using Free's formula. So the first thing I've done here in the notes is I've just done these conversions to make sure everything is now as a ratio. And because the very first gain block was the attenuator, that's why we see the minus 1.5 in here. The gain of the attenuator is minus 1.5 dB, and then that comes out to be 1 over 1.41. And then the noise figure, which is identical to the gain, or to the attenuation, because that was what we showed on the previous page, that an attenuator and the noise figure associated with it are identical. So we take 10 to the 1.5, which was the attenuation value over 10, and that gives us the noise figure for the attenuator as a ratio, 1.41. And then so on for the rest of the components, just working down, converting everything to ratios. Once we have that done, then we can use Free's formula in the noise figure form. So you have to go back to the equation just to remind yourself of how it works. The very first entry is all by itself, and that's the noise figure of the very first stage. And in this case, because we're dealing with an attenuator at the very beginning, we're going to get a number of 1.41 at the very beginning. Remember, a perfect noise figure would be 1. So you can't get anything less than 1 for a noise figure where we're talking about a ratio, or 0 dB noise figure is what it would be. But as a ratio, it's going to be 1. So we're already paying a price in noise figure because we've got 1.41. We're significantly above 1. And then we come in to get our second term from Free's formula, and that says it's got to be second stage's noise figure minus 1 over the first stage's gain. So the second stage had a gain, or noise figure, 5.01. Subtract 1 from it and divide by the gain of the first stage. And the gain of the first stage in this case is less than 1 because it's the attenuator. So that's also a very sad situation, because now that says because the first stage is actually a loss, the noise figure of the second stage is really going to hit us hard in this case, because this numerator, let's see if I can get my pen to work again, that's going to be 4.01, and now we're going to multiply that by 1.41, so we actually get a really large noise figure addition just because of that attenuator sitting there. And then things start to calm down a little bit when we go to the third stage. We take the noise figure of the third stage minus 1, and then we multiply the product of the gain of, this would be the gain of the second stage, and then 1 over 1.41 is the gain, of the first stage. And then we move on to the next stage, which we only have 4 stages in this case. We have 3.98 as the noise figure, and then we're going to have the product of all 3 gains. So this will be G2, G3, and then G1. It just happens to be the way I wrote the math out. And then we get the contributions from everything, and it works out to be 7.19. And then we convert that to dB as 10 log 10. I feel like I need to have Python running here just so I can do some calculation verification. I had restarted my system, so I need to go open up another shell. Activate the right environment, and then I'm going to launch the Qt console. And I'm going to do Control-Shift+ to make the fonts plenty big. And then I'm going to go and move that over to my second desktop. So it's sitting over here. And then I'm going to run PyLab, so I get NumPy and plotting installed. That ought to be pretty good for our purposes right now. I won't load any other packages, but I just wanted to just do a quick verification, 10 log 10 of 7.19. 8.567. When you take your exam, you'll probably want to be using your calculator because it will be a lot more compact device to use. So then we can go on to get the noise temperature, effective noise temperature, by just doing the conversion that I was talking about, which is this guy right here. Use room temperature T0 unless told otherwise, and then you get 1796.3 degrees Kelvin is the effective noise temperature of the receiver cascade. So that is all of this stuff in here is effectively at that level of noisiness, 1796. Now the thing that's amusing about this is that's not to touch, right? It's not like you're going to touch this front end and you're going to get burned by that huge temperature, 1796. It's just a measure of the noisiness of the front end, and it's just telling us that it's very noisy, mostly because of the fact that we have that attenuation up front, and then followed it with an amplifier that had a fairly high noise figure as well. So what we could do now is we could, to improve the system performance, is interchange the cable and the RF preamp. So now the first stage has a noise figure as a ratio of 5.01. And then we have the noise figure of the feed line, 1.41 minus 1. But the gain of that low noise amplifier is very high, which is very nice. So pretty much what's going to happen in this case, because we have a high gain preamp with a not super phenomenal noise figure, but it's not bad, super bad. See, when we get all the way done, adding in these other components, because we get so much gain of that very first stage, we had a gain of, 20 dB, right? So this gain of 20 dB is a ratio of 100, but that tends to minimize the impact of the noise figures of all the remaining subsystems. It would only be nice if we had a lower noise figure on that preamp, but the 1.5 dB of feed line loss, it kind of gets minimized very nicely by interchanging or having the preamp up close. I did one of these installations for cable for TV in my house a long time ago. It didn't work though. What didn't work about it was I had the phantom feed, I had the preamp, but the problem is I sit on the backside of a bluff that's just east of the university, and I'm set down in kind of in the trees. I mean, I'm looking at a little forest of ponderosa trees as I look to the west and to the south, and it's the bluff that I'm looking at. I have no line of sight to Cheyenne Mountain, which is where all the TV antennas are. So I wanted to get some of the diffraction coming over that bluff, but the problem is there's things behind me that form multipath, so I have a very bad multipath problem at my house. And shortly after we moved in, I tried this setup, and it just was still too much multipath on the TV signal, so we ended up with cable TV and have had that ever since. But some of you live in Colorado Springs where you can get by with an antenna on your TV and receive from Cheyenne Mountain directly because you have a pretty good line of sight there.
That's how that works.
What?
Oh. I bought a Samsung TV used off of Craigslist, and then it came with a little, like, white, it looked like a white piece of paper with a little wire running to the TV with a coax.
Okay.
That's what that is.
What, for putting an antenna on?
Yeah, it's free cable. That's how that works.
Well, it's not
Yeah,
free.
there's an HD antenna for the HD stations that they started broadcasting, 2012 or something like that?
You're talking about HD?
Yeah, the HD transmission, that's what that flat piece of paper one's for. I've got a giant one that I put in my attic to get everything up from here and from Denver.
I mean, I don't watch TV, but that's pretty cool to understand. They're just sifting for free. I like that.
Well, that's the way it was when I was growing up. Cable TV was a luxury, and it was an unnecessary thing until certain things started to happen, and more than one thing happened, right? I mean, it wasn't just the local broadcasters got cut out of the action, but the cable TV programming expanded very widely, and things like CNN and ESPN, sports and all those other things just came into being, and then everybody grew up around the idea that you have to have cable because you want to get all these other national programs that your local stations can't provide for you. It's quite the paradigm shift, I guess is what I would say, because I grew up with 3 networks, an ABC network, an NBC, and a CBS, and then there was an educational channel, and those were the ones we could get with an antenna pointed. Well, I grew up in Wisconsin, so the TV stations were in Green Bay, and I lived close to Green Bay, so we'd point the antenna towards Green Bay, Wisconsin, and that's how we'd get our TV. Interesting, because you guys don't, it's much different from your point of view than it was for me, but I'm okay with it. There has to be something for being old, seeing something that you just don't have anymore. But yeah, some of you probably do that. If you watch TV, you don't want to pay for cable. But nowadays, if you want to get data service, you have to have something, and we have that bundled together, right? TV and data from the cable company, Comcast. And we don't have any telephone company provider other than our cell phones. And that's been another major paradigm shift, right? I bet almost all of you don't have a landline wired anymore in your house. True?
Well, not a working one.
Okay. That was...
Yeah, until a couple of years ago I had one for emergency purposes, because that's how I am, but yeah, no, even we gave up on that after a while.
Yeah, well, you pay taxes on everything too, and not just sales tax. You're paying taxes for the service because of the infrastructures and everything, all the things that the government has tacked on that goes along with it. Okay, in the second example here, I didn't do the noise. Let's see, what did I not do? I didn't include the antenna noise temperature. So all these first examples just focused on the box. So the box being the cascade. And in this case, it was 4 elements. So we had option 1 was feed line up front. Option 2 was swapping the feed line and putting the preamp right there. So we got the temperature down to 1202. But now what we want to do in the next example is we want to work the entire system and model the antenna as having some noise temperature as it looks out into the sky and the environment. And then we'll be able to actually get the noise power at the output of the cascade. So here we have a noise temperature of 400 degrees Kelvin for this antenna, and it's not pointed to a really hot spot in the sky like at the sun or something. So this is 400 degrees Kelvin, and then we run through the same example we just did, so we don't really have to do anything more, except what we're going to be doing now is we're going to be using this formula that we saw before, where we're going to bring in our equivalent noise temperature, and we could get that in working this problem from the noise figure if we didn't have the noise temperature already calculated. And then we have the noise temperature of the source, which is in this case the antenna. Then we need the gain of the cascade, Boltzmann's constant, and then we would generally have a bandwidth that we would be dealing with. You know, for AM and double sideband, it would be twice the message bandwidth. For FM, we'd use Carson's rule. If it was digital modulation, we'd use some other formula to say it's twice the main lobe, or it's the main lobe of the spectrum's bandwidth, and those sorts of things. But that's where B would come from. So we can now put that stuff together. This is the cascade gain. So before I go on to do that, I'm going to do something that is common in the modeling and is also something I put on the review sheet. It's a handy simplification, and what it is, it's grouping K and T0 together because they kind of are from the physics of the problem, Boltzmann constant and the room temperature in Kelvin, and then putting the temperature ratio together. So in other words, we've added in a T0, but now we're going to put a T0 in the denominator over here and put that with the other temperatures. And so that's the ratio of source temperature, effective temperature of the cascade, normalized by T0. And when you do that, and then you want to do everything in dB, then you can, because we've got multiplication going on in here, now what we can do is, rather than multiplying all those numbers out and finding what 10 log base 10 is, we can just take the gain in dB by adding up the gains of the individual elements in the cascade. So that ends up being 86.5 dB. We can take KT0, which was that number, remember, that my professor made me commit to memory at room temperature. It's minus 174 dBm per hertz, and the room temperature is the 290. So we've got these two values already done, and then we just bring in the antenna, we bring in the noise temperature effective of the cascade, and then we throw in our 290. So that's a term that we have to calculate, have to take 10 log base 10 of that ratio, and then we have to take 10 log base 10 of the bandwidth. So this is the bandwidth term over here. So that's the bandwidth contribution in dB. If we look at this product up here, this is the product of 4 terms, but it's sum and I think somebody told me electrical engineers don't like multiplication. I mean, they'd rather do addition if they can get away with it, and that's where dB is really handy. So we can get away with not a lot of other math because not a lot of multiplication. We do have to take logarithms though. We do have actually a division, but maybe that's just dry humor. That's not very funny. At any rate, minus 28.71 dBm, and what forces this to come out in dBm is this guy. This thing has units of dBm per hertz. This has units of hertz in the log sense. And then the others, these are just dimensionless, so that's just dB. This is just dB. So when you look at how dB in the units work out, the dBm is the only thing that remains because the hertz cancel and the dimensionless quantities just raise or lower the dBm level. And I don't know if that's satisfying or if that's confusing, because if that's confusing to you, what I'm going to recommend and what I recommend at the end of the review sheet is then don't do it this way. Instead, just do it like it's shown here. Just multiply everything out, and then you can see clearly that the units are proper. I mean, KT0 is going to be watts per hertz, B is going to be hertz, so the units hertz are going to cancel. Ratio of temperatures is dimensionless, and gain is dimensionless, so you'll get something in terms of watts or milliwatts, and then to get it to dB you go 10 log base 10 of watts to get dBW, or 10 log base 10 of milliwatts to get dBm. I can't tell you how to choose that though. My preference is to work with addition and subtraction. So now to follow on with this question, if we were designing a system, we knew that we'd made a bad choice actually. We put the lossy transmission line up front, but so we're paying the price. We have more noise power right here. We have minus 28.71 dBm. For those of you that were in the lab earlier in the semester, just think of the spectrum analyzer. You'd be seeing a noise floor on the spectrum analyzer that would be, if it was put into a noise calibration mode so it can make a noise measurement, it would be reading minus 28.71 in a 100 kilohertz bandwidth if we had that capability. Our analyzers, I don't think, have that capability, but I've used analyzers that have spot noise measurement capability. Actually, it measures it in dBm per hertz, but there's different tools that are out there. At any rate, that's the noise power. Now suppose we would like to get a signal to noise ratio of 20 dB. So that means we'd like to have the signal power that comes all the way through this cascade be 20 dB above minus 28.71 dBm. So what that says in math terms is we'd like 10 log base 10 of the received signal. This is the received signal power. We'd like to have that be 20 dB above the noise power, and we're doing this calculation at the back end of the receiver, so we're going to take into account the noise figure of the receiver. So we're going to take and gain up the power at the antenna by GA, so this is now at the output of receiver, and then PNA is the noise power available at the output of the receiver. So we want that ratio to be 20. So what we'd like to do is solve for what received power do we need to have at the input to the receiver front end. And so we write all of that math down, and what I did here is I just converted it all to dB again. So I said PS in dB is equal to 20 plus the noise power. So we want to be 20 dB above the noise power, and then we get to subtract out the gain in dB of going through that front end, and that's going to be then the signal power at the input. So just again using addition and subtraction, that works out to be minus 95.21 dBm. So that would be the power we'd want at our input to our receiver to get us 20 dB at the output. That's a pretty small power level. It's not as small as it gets though for operations of wireless devices and things, but it's fairly small. So that's that type of calculation. So the last type of calculations are just adding a little bit more realism into this and actually saying we're going to propagate from one location to another. So this measurement here was just at the receiver front end, saying we would have to have minus 95.21, but suppose we want to design from the transmit to the receiver and then all the way through the receiver front end with the noise. And that scenario could come up in a satellite relay link, point-to-point communications on the ground, transmission from Cheyenne Mountain stations down to the receiver that you hold in your hand, transmission from the cell tower to the cell phone you hold in your hand, that type of calculation. And of course, terrestrial types of links are also subject to multipath, so we're not taking into account the multipath effects right now and how that makes things worse. We're just going to take a simple example of a satellite link where we have free space or line of sight types of links without any other propagation phenomena going on that will mess things up. So we're going to assume an isotropic radiator, which is just a source of RF power that radiates uniformly in all directions. So we put in a transmit power of PT watts, let's say, and if it's an omni antenna, what it does is it radiates a spherical wave, and then the power flux that you get, or power density that you get at a distance d, is just going to be the total power painted over the total power divided by the surface area of a sphere of radius d. So that's PT over 4 pi d squared. That's kind of a familiar geometry equation, right? Surface area of a sphere, 4 pi r squared is what I always remember. So d is the radius in this case. That's the distance to where we want to put our receiver. And that flux density is watts per meter squared then. So that's what's impinging upon our bodies, let's say, from an omni antenna. But if we go with a different type of antenna, one that's got directivity, so that one can put power gain in a particular direction, then we define that as having some gain over an isotropic antenna. So the isotropic is the equal radiation in all directions. An example of a directivity type of antenna is an aperture antenna, like a parabolic dish, something of that sort. We generally don't have these on our devices except for satellite receivers, is where we usually see the parabolic dish, something that has an aperture that gives us an effective area that's gives us quite a bit of gain over the isotropic. So to define an aperture antenna, it would be an aperture area that's much greater than the wavelength squared that we're operating at, and lambda is that wavelength. And if we plug that together, the equation for an aperture antenna, this is a simple model, is 4 pi times the aperture area divided by lambda squared. That's just going to tell us what the gain is of the aperture antenna. This is a model, and you'd find this in an antennas book for sure, but it's just the model that Dr. Zemer used in the book. So power received by an aperture antenna is going to be the power transmitted times the aperture area. And if the transmit antenna is also an aperture antenna, then we can throw the gain in for that aperture antenna, which would be another term for the antenna that's transmitting. So we'll have this formula here, which tells us this is the power received from two aperture antennas. The transmit power gain of Tx, gain of Rx, and these gains are going to be relative to an isotropic. An isotropic has no gain because it radiates equally in all directions and receives equally in all directions. So it has some attributes that maybe are of interest, and the big attribute this has is it has what's called free space path loss, and that's the quantity lambda over 4 pi d squared. That's the effective loss that you have in going from the transmit to the receive antenna. And I think most of us would agree that we would be disturbed if we didn't see a d or r squared in there, because we just know that that's the spreading factor, the 1 over r squared or 1 over d squared type of factor. And then we have the effective gains of the two antennas, and then the transmit power. So this is called free space path loss, and then there's an extra factor thrown in here called the fudge factor, system loss factor, to just say there might be some feed line attenuation getting in and out of these antennas, or some surface roughness. This thing's not working for me right now. Taking my pen apart because it has stopped working. Sometimes the battery gets a little bit corroded and it doesn't work as well. Yeah, that helped it. Helped it momentarily. Now it's going to quit again. Yep. Oops, no, wait a minute. So that's just an extra factor. Nominally, if there was no fudge factor, L0 would be 1. That's just a pad, though, you can put in. And now we've effectively built a link budget because we've got power received in terms of transmit power, gain of transmit antenna, and gain of receive antenna, and then our fudge factor loss, which is this guy right down here. And if we take that, all of this stuff in this equation to a dB kind of formulation, so now power received in dB will be power transmitted in, say, dBm. Path loss, we've taken the square out of that in front of the log 10, so it's 20 log 10 of the ratio of lambda over 4 pi d, so that's our path loss term. And then we have the transmitted power, 10 log base 10, which would be like dBm. Then we have the gain of the transmit antenna, and when that's lumped in with the transmitted power, that becomes the effective isotropic radiated power, or EIRP. Then we have the gain of the receive antenna in dB, and then we subtract or reduce our received power by this fudge factor. So going through an example, if we have a link, say a satellite communications link, where we have an EIRP of 38 dBW, we're transmitting at 400 megahertz. This is a very low frequency for a satellite. We have the effective temperature and the receiver noise temperature combined of 1000 K. So this is for our total receiver package. So that's receiver as a whole plus the antenna temperature. The antenna gain, 0 dB, so this must be an isotropic antenna. And then system loss of 3 dB, received bandwidth of 2 kilohertz, and we're up in geostationary. We're at 41,000 kilometers. And it says here, find the output SNR in a 2 kilohertz receiver bandwidth. So there's two calculations that have to be done. One is to go through the path loss equation to see where all of this EIRP, where does that go in the free space path loss equation. So we plug that in here, all in dB units. We have the IRP, we have our path loss, our receiver fudge factor. Then we have the path loss term, which is over here. Putting that together, that brings us down to a dBW value of minus 141, but then if we add 30, that takes us from dBW to dBm, so it's minus 111.74 dBm. And side calculations are C over F, speed of light in a vacuum, 3 times 10 to the 8th over the 400 megahertz. Then the second calculation, so this is number 1. Second calculation is the noise power at the receiver, and that doesn't involve anything with the antenna gains, the path loss, or anything. It's just what the receiver sitting there is doing with its antenna temperature, TS, the effective temperature of the electronics package. Just plugging into that calculation type that we did earlier, we have the minus 174 dBm per hertz, which fits in there. We have path loss, not path loss, we have the ratio of temperatures, and then we have what the bandwidth brings in. The wider the bandwidth, the more noise we collect. So minus 135.62 dBm, and then subtract that from minus 111.74 dBm of signal power, and we're going to come out positive because it says we have more signal power than we do noise power. So we're at 23.88 dB, which is good. So we're done with a couple of examples on this, and now I have to use the rest of the time in some wise fashion. Any questions at this point before I jump over and just briefly take a look at the quiz so you can see how it lays out, and then I'll probably jump over to the review, because the review, I'll start at the bottom of the review and work my way from where we are today to the back into the past. So go look at this quiz. This quiz has got a couple of problems on it. It's very much like the examples we've just been going through, but this is a good example of what you'll find on the final. And you've also got some problems very similar to this in the homework that's due on Monday. So here you're just given as a word problem a noise temperature of 900 Kelvin. You're feeding a cascade that has an amplifier and a noise figure, an attenuator which has a noise figure equal to the attenuation, a mixer which has a noise figure, and an IF amplifier which has a noise figure. So that means we can use Free's formula to get the noise figure of the cascade and get the effective noise temperature of the cascade. So just like I did in the notes, I do convert everything to ratios for the noise figures and for the gains. So when you work an exam problem, make sure you do this. It's a very common error to not convert from dB back to ratios. So do that, and then you can plug in. And by the way, if you make this mistake, you always get an answer. It's just going to be a nonsense answer. The numbers will still fit into the math. Occasionally you'll see something weird, but it'll still go in and it'll punch out on your calculator, but it won't be the right answer. So you have to get things into ratios. So I just plug the numbers in. In this case, I get 1.28, and if I take 10 log base that, it looks like I did something weird here, though. I don't know what the difference is. I've got 1.28 and I've got 1.31. I need to run these numbers to make sure, or you can do that yourself and see why I have that difference in there. But if I wanted noise figure in dB, or I'd asked for that in the problem, you have to take 10 log base 10. And the noise temperature, you just convert with the 290 times the quantity f minus 1, and f has to be as a ratio. So again, ratio.
So the 1.31 is supposed to be 1.28.
You just ran the numbers?
Oh no, is it?
I don't know.
You drew an arrow between them.
I don't know. I have to run the numbers to make sure. I can do it. I can punch it all into Python right now, but I don't want to take the time. You know what I'd be doing. Do you want me to do it? I think you guys can do it. It's just a matter of doing all this stuff. 2 minus 1 over 100 plus quantity 1.58 minus 1 over 100 times 1/2. That 1/2 is from the attenuator. And then plus 3.16 minus 1.
You missed a parentheses on the second term.
Okay. Thank you. He's going to get mad at me probably if I don't do this right. Okay, so 3.16 over parentheses 100 times 1/2 times 10, 1.2859. So I think that tells me that this number is out, and this is 1.2859 would be 6. 1.286. And then, so what would the noise figure be in dB? It would be 10 times log 10 of 1.286, or I could just put the number in from up above. So 1.09 dB. It probably didn't make any difference in this problem. 1.28 and 1.31 probably still came out to be about 1.09 is my guess. Nope, it is bigger. So, yeah, my mistake in that solution. And then the other part of this quiz said find the SNR. So this is working through the received signal power. And taking that received signal power all the way through to the receiver output. So you're told that you're getting received signal power in dBm of minus 80 dBm, and it's going to be in a bandwidth of 1 megahertz. So now we just work the calculation. This is part 1, get the received signal power in dBm. And then part 2 is to go with our TE and TS and build that up into the noise equation that we've seen a couple of times, the minus 174. These are the gains all the way through. And this is the ratio of the temperatures, and then this is the bandwidth. And that ends up being minus 41.7 dBm, whereas the minus 80 dBm gets gained up by 10, down by 3, up by 10, up by 40 dB. And then we do the subtraction, and we're sitting at a dB value of 28.73 dB signal to noise ratio. The second part of the quiz, I'm not going to do that right now because I want to let you take a look at it. This is like the second problem we were doing in the lecture notes, where we're looking at a link budget. So in this case, the link budget is you want to find how much transmit power you need to achieve a 20 dB link SNR. So in this case, this is turning things around and saying, I want to get 20 dB SNR. I'm going to give you a bunch of information about the transmitter and the receiver, but I want to find out how much power I need to send out from my transmitter in order to ensure that I have 20 dB of SNR at the receiver. So you need things like the frequency, the gain of the antenna and the receive antenna, noise temperature, including the antenna. So in this problem, and an exam could come like this. This is TS plus TE. So in this problem, you don't have to use all the other calculations with Free's equation. This characterizes the receiver and the antenna all in one. So this just says we have it all built up for us ahead of time. Somebody's told us what that is. And you also know what the gain is of the receiver. The antenna is 10 dB. And, okay, this has got a twist in it. You don't need to know what the gain is of the electronics package. You're going to reference it back to the input to the receiver. So this is going to try to get the 20 dB right at the receiver. I'm trying to see what I'm missing here. Find the receiver output noise power. Find the total noise power at the receiver output. So in this case, you're not putting an extra gain on the receiver electronics. You're assuming you're just going to get the power right at the input side, so there's no gain. So it's just 0 dB in the equation. So there is no, the gain term is equal to 0 dB. The only gain term we have in the receiver is the gain of the antenna. So you can still work the problem, you just think of it as being 0 dB, so this should be dBm. No, let's see. That should be dBm because I was given dBm. No, what am I doing wrong here? Less power transmitted in dB, so no, that's right. It's not a dBm on there. This is just how much path loss you have in getting from the transmitter to the receiver. So it's just dB of path loss. So I say it's the received signal less the transmit power. We're going to get the transmit power applied at the very end because we want to find out what that is. So in this case, the transmit power was an unknown, but that combined with the -98 path loss all the way through with the antenna, the path loss, transmit and receive antennas. So those will combine together. And then we do the noise power calculation down below and find out that's minus 109.59 dBm. And then you finally come down to saying signal power in dB, or the dB, the attenuation of the receiver. You're going to have did this right. So we want to have the transmit power minus its loss and getting to the receiver, which is this 98.42. And then you want that quantity minus the noise power to sit at 20 dB. So we want to have a 20 dB margin. So if I look at how I did this, I'm solving for that guy right there. So I want PTX to be the 20. My colors didn't shift when I finger touched it. So we have the 20 that's already on the right side, and then we move the TX, and then we move the loss to the right side, which is going to be this value. And then we move the noise to the right side, which will be a plus value. So when you put those values in terms of positive values, that works out to be minus 8.83 dBm that you're going to be transmitting. And that seems like a really low dBm value, but that just tells you that in this particular scenario, we're only transmitting 10 kilometers. We're not going all that far, and we can get our desired 20 dB signal to noise ratio with only 8.83 dBm. Just think of the lab. You can very easily get 0 dBm, and then you can easily get 10 dBm with our lab generators. So what does that tell you? Somebody thinking quickly? You put the right antenna on a lab generator and you can actually transmit a fair distance. That's what it tells me. So you do have to be careful, and I do like using antennas in the lab, but I have to be careful that we don't get too much power out into an antenna that has gain in a direction, and we end up sending it somewhere that would get us into trouble, because that's what this link budget works out to be. It would go a fairly good distance, 10 kilometers. So I'm really way out of time. I want to go through the review sheet though, and then hopefully you've been thinking about when we could meet next week if we'd like to talk more on the project. Not everybody was on when I propositioned like that, but
an option would totally be to record just a little video, probably like a 20-30 minute something going over the review sheet.
yeah.
I know Dr. Simiari did that because he ran out of time today, or I think yesterday.
Okay.
Today? Yeah, today.
So
That's just an option.
yeah, I'd like to hit some high points, but I'd also like to know, would anybody like to have a session next week just to talk more about the project? And as long as I get a couple of people, that's all I care, because then I will do a recording and then I can push that up there. Is anybody interested in that? You can Slack message me, but I'd like you to message me on the comm channel so that everybody can see what's being talked about, and then if a couple people agree, we'll do it at a particular time.
Can I get back to you in a day or
Yeah,
so?
that's fine. I do
Perfect.
have, I'm giving a project final on Monday night, and I have a master's student doing a project defense on Monday from noon to 1. And then Tuesday I don't have any classes except the normal time this class would meet. Okay, I want to just take a quick look at this, and I'll think about making a video by myself, but I wouldn't mind having an audience. So this just gives you the layout of the final in terms of the material that we've covered throughout the semester. So that's at the top of it. And it starts with the oldest material. So now at this point I want to just flip to the back and say digital communications. There could be some conceptual questions on that based on what you learn in going through the project. It's not super likely, but there is a possibility. This is kind of a tutorial though right here, a really super compressed tutorial. So, and the exam has always been open book, open notes. So this information was available always, and it's just here, and it will be available again if I ask some questions on this material. It's not super likely, but then we move into free space propagation, and I summarize what we've been going through today on here, talk about how to work the equations with dB in general terms. So this can be useful. I put this together, so this is kind of like a miniature cheat sheet for working these problems that we've just been looking at. Another new material is characterization of noise in systems. That was the noise figure calculation and noise temperature that we just came through, and those fundamental concepts. So that will be on the final. Physical noise sources, really not much to write on. You saw an example of one of those types of problems on one of the old exam 2s. That's just KTB noise and Nyquist formula and Nyquist theorem. So I'm listing, really the only thing is thermal noise. And then as we go up the line here, you just see, and I'm going to stop here pretty quick, we just see another new for final is the general performance. That was that last picture. I could possibly put that on there and say, comment on this. I had some discussion on that in the lecture. Definitely the next one up the list, multiplexing. You saw the quiz from last week. You've seen the 2 old multiplexing FDM types of problems. So there'll be one of those types of problems. Another thing that I'm putting on here is digital time division multiplexing. That was covered at the end of chapter 3, but I didn't ask you a question on it, so that could appear now on the final. That's TDM. That's again a pretty straightforward concept, so I'm willing to bet you were thinking that would have been on this last example or last exam. And then as it goes on up the line here, I have things, but I'm not going to take any more of your time unless you want to ask me questions, because I know some of you have to get going. But if I do make a short video, I would spend more time walking through this. And as I go through each item, I will not take anything that says no problem on this and turn it into a problem. That's an assured thing. What I'm most likely to do, though, is take something that's not likely and make it will not be on the exam. I'm also likely to say something that is problem on this is likely to problem on this is certain. And in that scenario, it would be something, say, on exam 2, where there were some common errors by essentially everybody, that, and I would say for that type of problem, I'm not giving the example right now, I would say, no, this I'll definitely retest on because this didn't work well in the exam. And that's some of the FM stuff that we did. But I have to bring it back into memory which of those types. So I will get it back in my head when I go study the old exam. And nobody sent me any thoughts on that, so I'll come up with it though. Anybody want to ask any project questions? That's the most important thing for having another meeting, is to just go over some more things on the project and try to get your heads set straight on that. Because it's pretty simple to do, but you've just got to spend time on it. The notebook is there. Follow my directions. I've improved the writing on that, so I think I've made that even better. I'm just not an English major, that's all, so my writing is always not very good.
I'll have questions for you on that tomorrow. I gotta give my presentation for senior design tomorrow.
Yeah, well, senior design tomorrow takes up just about 2/3 of the day, right?
Yeah, but it's been my intense focus for the past couple of days is getting our presentation polished and ready to go.
I reviewed one today, and then they told me they couldn't use my comments because they'd already recorded it, and they can't go back and do it again, or they don't want to go back and do it again. So at least they know what I'll ask them. But
right. Are you gonna be there?
I'm going to
first
be
thing in the
there for
morning?
part of it. I'm not going to tune into everything because I've got a lot of stuff to do, but I'll have it running since it's going to be on Teams, right?
It will be on Teams.
I know you're first, but then there's demos at 1 o'clock, starting at 1 o'clock, is my understanding.
Yeah, we'll have a demo too.
It's a grueling thing, is all I can say.
Chris, my man, you sound tired as hell.
I was up until almost 3 this morning, and then I got up at 7 to get my kids.
Fellow man of culture, I see.
Yeah.
Well, I had another student in my real-time class who wrote me a message at 4 in the morning. Had some really disappointing news, but yeah, I see that. When I see people are writing messages in those times of the day, I'm like, wow. I don't get up that early, and I'm not still up from the day before at that time either. Okay,
Man, you gotta do. It's time to graduate
yeah,
in the show.
time to go somewhere, right?
Yeah.
So I will do this, but if somebody was to say, I'd like you to, I'll be here for Slack at this time, and I had a little audience, I would go through this gladly with somebody else rather than me recording in silence.
With examples, maybe?
Well,
I'm just saying, I'll be more than happy to jump on anytime next week, but next Tuesday would probably be the best.
Okay.
At the normal time. That's what I was going to suggest in Slack, but I'll just go ahead and say it audibly here now, so everybody
well,
else
put
can
it
hear
on Slack though, so you're the first person to propose a time, and then others can say, start here and end here, or something like that, because I can move it around either direction conveniently, so I can get the most people next Tuesday. And you're going to be working to get the homework in by Monday. The original idea for that was I would have a grader get it graded, but I still want to have it Monday because I don't want you to be messing around with that when you got the project to be working on. At least I think that's when it's due.
So on your website says homework 12 is due on Friday, tomorrow.
Okay.
Is it going?
That's
Yeah.
right, it was due on Friday. That was so the grader could grade it and you could have it back. But
Okay.
I'm not going to be grading it tomorrow. I'm going to be doing some capstone stuff. When
So are we still submitting tomorrow?
when do you want to have it due? Because you just got to practice the material.
Yeah, I can do it tomorrow. That's fine. Just asking. You were saying
Okay.
Monday, that's why.
Okay. So I'm going to leave it on Friday. It can be late, which for some of you will be at about midnight. So how would that be? Just so you can get it off your chest and be on.
Yeah, I think that's fine.
Okay. Well,
Honestly, I haven't even started looking at the homework yet because, again, a project and senior design.
okay. So Jared, you said sounds good. You're saying sounds good to the homework or Chris's posting of meeting on Tuesday? Both. Okay. Okay. Very good. Thank you. And I'm going to get my video shut down here and then go see who's still left on.
All right, thanks, Dr. Wickert. I'll catch you